So there were few things we did not discuss in the last lecture, and one of them was that we did not define properly the sign of the angular acceleration. So we said if there's a disk moving like this, it has an omega, then the vector omega is out of plane, that is in this direction. And if d omega over dt is greater than 0, then, which means it's increasing, then alpha is also out of the plane. And similarly for the negative direction, not negative direction, for the other direction, omega is actually in the plane, or going into the plane, and if d omega over dt is greater than 0, alpha is also in the plane. You can have other cases also. If like for this case, d omega over dt, if it's less than 0, then alpha is inside the plane, and here if d omega dt is less than 0, then alpha is up the plane, similar to the case when we discuss about velocity and acceleration. Now some of may get confused whether it's positive or negative or not. Well, plus, positive or negative, and a vector becomes positive or negative not because of direction, but the way we define the axis system. So if we define this as the plus axis, let's say the plus y axis, then this vector is positive, this vector is positive, but this vector is negative. And similarly here, if we define y as this axis, then this vector is negative, this vector is negative, and this vector is positive. So the vectors assume sign negative or positive because of the virtue of the way we have defined the axis system. Plus and minus has nothing to do with the vector itself. So please don't get confused. In the plane and out of the plane makes sense because we know that is a direction, but we really can't say it's a plus vector or it's a negative vector unless we do not define an axis system. So this is an important point to understand. And in the last lecture we missed out explaining torque. So let's say we define an axis in the plane, that is this axis about which the object is moving, and we also said that torque equals I alpha. So I is a measure similar to mass, so it's easier to move this object in an angular way compared to this object in an angular way. Let's say this is heavy and this is light. So for this guy, if I is I1 and for this guy I is I2, then I1 is less than I2, which means easier to move angularly this guy than compared to this one. So I is sort of a measure of mass. It's easier to give acceleration to a smaller mass than to give acceleration to a bigger mass. So that's a measure of giving angular acceleration, alpha. So alpha equals tau over I. So alpha depends on how big or how small I is, where I is a measure of the shape of the system. So I is small here and I is big here. What else alpha depends on? Alpha depends on torque, tau. Now how is torque defined? Now this guy will not start moving unless you apply a force to it, F. Only then it will start moving, and you have to apply a distance R. And torque, and let's say the angle between them is 90 degrees. Then torque is defined as R times F. That's all. You see? Okay. Now if you why is it like this? Because if you increase the force, then torque increases, and as torque increases, alpha increases. So it makes sense that torque is defined like this. I mean we really can't prove that torque should be defined like that. It's just a definition, but we know that torque should depend on force, and it depends like this. So if you increase F, torque increases, and as torque increases, alpha increases. Also, where do you apply force? You might have seen door. If you apply a force, let's say into the plane here, it's difficult to measure to move the door. But let's say if you apply the force here, then it's difficult to measure. It's difficult to move the door in this case. So you see, it also depends on where you apply the force. This is radius R1, this is radius R2. So R1 is less than R2, so you can see torque is more for this point for the same force compared to this point. So you can see that torque depends on radius also. Okay, there's one more factor which we need to understand, and which is this is fine, but it may happen that you can apply a force like that instead of let's make a new diagram. It may happen that you can apply a force like this, or let's make it clear, maybe like this, where it makes an angle theta. Then, as a matter of fact, if you apply a force like this directly pointing towards the center, you're not really going to move the system angularly. You see this point? So it also depends how you define how you apply the force. So here you see, so if this thing makes an angle theta and this is force F, you can break this vector into two parts. This is going to be F cos theta, and this is going to be F sin theta, because the way you define theta, it becomes F cos theta and this becomes F sin theta. If you call this theta, then this becomes F cos theta, and the other one becomes F sin theta. So it's only this part of the force that is going to make the system go round or move angularly. And for here, this part of the system is zero, because there is no component of this force in the perpendicular direction or in the tangential direction. And this component is the tangential to the point where you are applying the force, tangential component. So let's call this tangential component as F perpendicular. So as a matter of fact, torque is given as R times F perpendicular, right? So this is the definition of torque. Torque, which is responsible for producing an angular acceleration, depends on radius, how far you are from the axis you apply the torque, and also on the force that is moving the object. So we'll discuss more examples to understand what's going on.